Hello, everybody. So my name is Nader, and I work for Intel. My colleagues Amir and Hassene also joined me today to talk about a highly efficient SVT-AV1-based solution for VOD application. In this presentation, we will go through the recent development work for SVT-AV1 encoder, including CRF mode and VBR mode. We will then present an evaluation results for the SVT-AV1 encoder as compared to other open source encoders where the evaluation was conducted using several approaches based on the dynamic optimizer framework. A fast evaluation approach that offers a significant complexity reduction of the dynamic optimizer is then discussed. And finally, we will present the concluded remarks. As you probably know, so the SVT-AV1 encoder is already adopted as a production reference software by the software implementation working group of the Alliance for Open Media in August 2020. And the encoder is open sourced and it's available on SVT-AV1 repository on GitLab. In the few last months, several complexity and memory footprint reduction features have been adopted, which allowed us to add other presets from M7 to M12 to cover faster speed ranges. We also noticeably improved the coding efficiency by introducing several quality features such as TPL and content adaptive prediction structure. On the rate control side, a multi-pass rate control was introduced that showed good quality complexity trade-offs. Talking about CRF, so we have improved the CRF mode by adopting a two-pass encoding approach, where an IPP flat prediction structure is used for the first pass, and it is designed to be configurable to obey to different quality complexity trade-offs. The output of the first pass is mainly used to select the suitable prediction structure to be used by the second pass, and the generated statistics by the first pass are also used to improve the encoding of the input video in the final pass. Another major feature that noticeably improved the quality provided by SVT-AV1 encoder is the temporal dependency model, or TPL, which is used to improve the quality through QP scaling and QP modulation. TPL information is also used to reduce the complexity of some expensive algorithm in the mode decision in a way that a fast version of the feature is used for low propagated areas, and the full version of the same feature that provide a higher quality is used at highly propagated area. We also finalized the multi-threaded implementation of this feature, and we made it configurable depending on the use case. So the results of this improvement will be presented later on by Hassene, and now I'm gonna give the floor to my colleague Amir to talk about the VBR improvement.
Thank you, Nader, for the introduction. My name is Amir. In the next section, I will talk about the new multi-pass VBR algorithm, which was designed for VOD applications. So what is the difference between CRF and VBR? In CRF mode, we specify QP level, then the algorithm assigns the QPs or Q indices per frame to get a constant quality. The QP assignment uses the complexity of each frame. After the clip is encoded, we get the actual bitrate. But there are some applications where we want the encoder to encode the video at a specific target rate. So using CRF might be very costly for us because we need to perform multiple encodings. To solve this problem, we use rate control. In rate control mode, we specify the target rate as an input to the encoder, and the rate control algorithm assigns the QPs per frame or blocks to achieve the target rate. Since there are rate constraints, the overall quality of VBR would be lower than CRF, which has no rate constraint. In our latest VBR algorithm in SVT, we have designed a multi-pass algorithm that minimizes the quality gap between CRF and VBR while maintaining the target rate constraints. As you can see in this slide, there are three passes. The first pass is a simple and fast IPP. which is common between CRF and VBR. The output data from the first pass is used to find the prediction structure and also the input QP for the middle pass. The middle pass is a CRF encoder, which is much faster than the final pass. And at the end, we have the final pass, which uses the statistics from previous passes to assign the final QPs. So in the middle pass, the goal is to find the rate distribution of the clip over different gobs, mini gobs, and frame, assuming there are no rate constraints. So we run the middle pass in CRF mode. In this way, you find the part of the clip which use more bits and the parts which require fewer bits. To get a better estimate, we use the target rate and statistics from the IPP pass to find an input QP for the middle pass. Of course, this is a very rough estimate, but the closer we get to the final pass, the better estimates are provided. The middle pass is a very fast encoder that has similar prediction structure as the final pass. The most important stored data is bit per picture and the corresponding Q index. In order to make the middle pass faster, some speed optimizations are done. For example, the input video is downsampled, some of the non-reference frames are bypassed, and other features like filters or warp or OBMC are shot. And overall, the MD is simplified to use limited references and limited modes. After running the fast IPP and the middle pass, the statistics are sent to the final pass. Based on these inputs, the final pass assigns target rate per gob, mini gob, and then per frames. For example, in the first gob, we use the actual rate of the gob in the middle pass, actual rate of the whole clip in the middle pass, and the target rate of the clip to find the target rate of the gob by using cross-multiplying, as shown in the slide. After gob rate assignment, we assign the target rate per mini gob using the same concept. And the rate of each mini gob is then distributed between frames by considering the feedback from previous frames and the current state of the rate control. So the next step is to map the rate into a Q index. Similar to CRF, TPL is used to find the range of Q indices. Then the rate control algorithm finds the QP index that has closest rate estimate to the target rate in the provided range. After the rate control is done, the encoder performs mode decision based on the assigned Q index. After all the blocks are encoded, the estimated rate of the frame is compared to the target rate. If the rate does not satisfy the rate constraints, the algorithm decides to do a re-encoding with a new Q index. In general, re-encoding can be very costly. However, based on the flexible design of the SVT encoder, only mode decision part is done again. And there is no need to redo the components like motion estimation, entropy coding, or filters. And finally, when the frame is completely encoded, a feedback is sent to the rate control to update the internal model and make required adjustments for future frames. So to summarize, we have designed a multi-pass algorithm to close the quality gap between CRF and VBR while maintaining the rate constraints. Also, the first two passes are optimized heavily to achieve low speed cuts. We will go over the speed versus quality results in the next section. My colleague Hassene will continue the presentation. Thank you.
Thank you, Amir and Nader, for the going through the first set of slides. My name is Hassene, and I'm gonna try to go through the setup experiment for the experiments that we ran, along with the performance validating or showing the performance of SVT-AV1. First of all, I wanted to go through the shot-based encoding setup that we used for these tests. Video clip is split into shots, downsampled into multiple resolutions. We picked 8 resolutions starting from 1080p down to 144p. All of the encodings or all of the shots are encoded at multiple CRF values, decoded, upsampled, and then the distortion metrics are actually measured on the original resolution. The bitrate and distortion pairs are then passed into a convex hull computation tool, and 3 sets of convex hulls are generated and used towards the BD rate calculation as compared to a reference encoder. For the test set, we have used the El Fuente open source Netflix content. It has about 8 minutes at 30 frames per second. It was split into 140 shots. On average, there's about 3.5 seconds per shot. And we used 8 resolutions going from 1080p down to 144p at 11 CRF values with slightly different ranges between AV1, VP9, and AVC, HEVC, and VVC. To collect the metrics, we used the open source VMAF application, the collected PSNR, SSIM, and VMAF. Following the command line that you see on the slide, we have then measured the BD rate differences after taking the convex hull of all of the possible combinations, then average the BD rate for PSNR, SSIM, and VMAF so that we can represent them all in one graph. As for the complexity metric, we have used the user bin time utility from Linux, collected the user time, added up to the system time, for the representing the total encoding time per executed command line. Now, going to the one of the exciting parts, always for video codec experts, which is looking at graphs and numbers. And so the graph that we have here represents a comparison of trade-offs between multiple video codec implementations. We have selected open source implementations. For AV1, we've selected the libaom CPU0 as a quality reference for this graph. We have selected libvpx for VP9, X265 for HEVC, X264 for AVC, and VVEnc for VVC, and ultimately SVT-AV1 also for AV1. Now, every color on this graph, as you can see, is an encoder implementation. Every point on each of the curves is a quality versus complexity trade-off, which is also commonly referred to as a preset. Excitingly, we see that SVT-AV1 is now spanning from the M0 being in the higher complexity, higher quality range all the way to M12, which is now reaching X264 very fast speed levels while maintaining a good 25% BD rate gain. M12 is also, if we are to draw a horizontal line, would be at the similar quality level of X264 very slow, while being many an order of magnitude faster. So with this being the CRF performance of, or comparing the CRF performance of all of the encodings, we want to go now to evaluating the VBR performance of SVT-AV1. To do so, we have gathered all of the CRF encodings results, contributing to generating 8 different quality levels, as has been discussed in the SPIE paper that you can see the link for below. We have selected for those 8 quality levels to be matching VMAF 95, 90, 80, 70, 60, 50, 40, and 30. We have then generated the average resolution and CRF for the final streams that would yield those quality levels, and ended up with the table that you see on the slide. Then we have taken the VBR mode of SVT-AV1, and we have ran the encodings to match the average bit rates generated by the CRF mode. Going to the results of this comparison, we could see that on this slide we have the VBR encoding results in the blue curve per preset, and then we also have the CRF encoding results on the red curve. We could see that VBR is only a few percent away from the CRF results. The x-axis on this graph representing the total encoding time, the y-axis representing the average PSNR SSIM VMAF BD rate deviation as compared to M0 being taken as a reference here. There's also a little bit of a slowdown for the VBR encoder, and as this is a work in progress, we are continuing to optimize the cycles trade-off of the VBR mode to be as close as possible to the CRF mode. Now, going to this section, we wanted to actually show the benefits of using SVT-AV1 within fast parameter selection for convex hull encoding. This method specifically uses a fast encoder preset as a first pass across the resolution and CRF points. Then we perform a re-encoding of the ultimate convex hull points or the selected convex hull points using a higher quality presets. We ran all of the combinations of fast preset and target quality presets for all of the presets that we have in SVT-AV1. Then we show here on the graph that the red curve is the initial traditional way of using one preset per encoding, and the green curve is the convex hull of all of the combinations across all of the presets using a fast preset, then a slower preset, or a higher quality preset. What we can notice is with a very high granularity of quality versus cycles trade-offs that SVT-AV1 features, we can show that the green curve would yield a speed up of about 1.2 to 9x while maintaining the same quality levels. We can also see that the final encoding preset does not really always have to be the target preset. So for example, using M11 as a fast pass and then M6 as a target quality level could be used to achieve the same quality level as M7 while also speeding it up by at least 3x. To conclude, we see that SVT-AV1 now features 13 quality speed presets going from M0 to M12, extending its supported complexity range from the high latency and premium VOD to the low latency streaming and gaming applications. SVT-AV1 also helps to save bandwidth, as we can see that M12 is about the same complexity of X264, very fast, while maintaining a 25% lower bandwidth, while M12 is also 14x faster than X264, very slow, while maintaining a similar quality level. SVT-AV1 supports both CRF and VBR in a VOD-targeted encoding modes, and using fast encoding parameter selection for convex hull encoding, we see with SVT-AV1 we get a speed up of 1.2 to 9x while maintaining similar quality. As always, we wanted to acknowledge and thank everyone for that contributed to this work, both on the design and algorithmic and implementation level, and preparing the encodings and data collection and analysis for this presentation. We also wanted to acknowledge the Intel SVT team for their continued hard work and dedication to the SVT-AV1 project. We wanted to thank the co-authors of the SPIE paper of the Facebook and Intel teams, which was the initial step for this work. And last but not least, the AUM and SIWG members for their contributions and support for the SVT-AV1 project. Last but not least, we wanted to share briefly the encoders, versions, and command lines used for these tests, and the software and hardware configuration for the shot-based encoding. Thank you all for your time today attending our presentation, which I hope was both informative and insightful for where SVT-AV1 is at this point. Thank you.
And we're back for our last Q&A session of the day. I am joined with the three great speakers, Nader, Amir, and Hassene. Hi, guys.
Hi.
Hello.
Nice to meet you all. Let's just get right into the questions. I think this might take a little while. We've got three people to respond to each question, so we'll save all the time for you guys. First one is, do you use any ROI-based approaches for encoding to speed up or optimize quality?
Okay, so I can take this question. So, yeah, for sure. So we use some ROI approaches. For example, we use output of the TPL to increase and decrease, enhance or degrade the quality.
Sorry, it's a bit difficult to hear you. Sorry to cut you off.
Sorry about that. Okay, how about now? Okay, so yeah, the answer is yes. So we use ROI approaches to improve video quality and speed trade-offs, such as TPL or first pass encoding statistics. Yeah, so the answer is yes. We use that.
Great. Yeah. The next one here is about UGC content. So how well does it perform on UGC content, or in general, non-pristine studio content?
I'll take that one and invite whoever's asked the question to take a look at the SPIE 2021 paper, where apart from the content that we just used, which is the El Fuente Premium VOD, we've used a set of YouTube UGC content across different resolutions or different frame rates and different everything, and the trends are about the same. So the graph that you see is very representative to the performance that we see on UGC.
Great. All right, another one here is, what's the primary focus for SVT-AV1? Is it VOD to begin with, or is it also relevant for various live use cases?
Right, the target, I'll take, and then you can comment, Nader. So the target is to actually spend for everything. We are starting with UGC right now as an initial focus, as you saw in the presentation, because UGC is usually the, or VOD is usually the initial, initial place to start with the new codecs. But SVT-AV1, especially now with its latest presets, is more than capable of adopting or being applied to live use cases. Nader, you can.
Yeah, that's exactly that what I was gonna say. And our target is to build the full palette of the quality speed trade-offs and give it to have it to the user to choose whatever he wants, whether VOD or streaming or gaming application.
All right. Next one's from the audience, from Ranjit. And sorry for the other folks who've been asking questions. I haven't always been reading who's said it. Sometimes reading it too fast, so apologies. But from Ranjit in the audience, does the encode time of SVT-AV1 VBR include all the passes, like the middle pass? Because VBR seems to be comparable with CRF from the comparison.
Yes, it includes everything. All three passes are there. As I mentioned in the presentation, they are highly optimized. So they are only a fraction of the final CRF pass.
All right, pretty straightforward. So looking beyond AV1, how do you, and maybe it's a question for all three of you, you can all take a stab at this one, but how do you envision the state of the art of video codecs looking forward?
Well, do you want to?
Okay, so let me start. So I think we will always need for better compression, right? So video codec, they're gonna always taking the main place in the video pipeline. So, and then we need to work harder to get that to save on bits, like bits is money at the end of the day. Yeah, go ahead, Amir.
Yeah, what I wanted to add is basically there would be more content, there would be higher resolutions, we will go to 8K, 16K, and we will need better or more complex video encoders. But as we grow, there would be more computation resources for us. I would expect that we will have the same game going on, that we will have more compute and we will have more complex standards coming.
Yeah, although I like to see new codecs and work on them, I'm seeing that the adoption curve of codecs is slowing down a little bit. So we see that AVC is the dominant codec at this point. We're hoping for AV1 with its royalty-free nature to, take that podium a little bit and carry on to that. But it seems like, and now that we are moving to at-scale video, there are a lot of problems that could be solved at a higher level, at the solution level. So you just need a good enough codec and quite some smart ideas to be able to gain video compression, as we see with the dynamic optimizer, reduce the speed, as we could see with the fast convex hull optimizations, or the hardware speed up solutions, as was discussed a couple of or a few talks ago. So all of these are working based on the same codec, but trying to improve and get the quality much better, or the speed much better, which I think we are just scratching the surface on. So maybe there's a lot to do there before going on to next codecs.
All right. I think that just about does it for the Q&A here. So thanks to all three of you for joining once again. This is a great final talk to close us out. Any last statements, any of you or all three of you?
Yeah, thank you for having us. Looking forward to other events. Thank you.
Absolutely.
Thank you.
Great. So with that, we are wrapped up with our talks for the day, but we do still have one event left, which is our live panel. Now, to remind everyone, this will be on the topic of the importance of audio, and have panelists from across the industry. So after this short break, we will be cutting over to our panel hosted by Mana.